Hello, this video presents our work on cross-language clone detection for mobile apps called Step. This work was presented at the 26th Ibero-American Conference of Software Engineering and is joint work with Stephanie Jimenez, Gordana Rakic, and Silvia Takahashi. First of all, let us present the idea of code clones, which corresponds to identical codes found spread around a code base. In this case, we are showing the example for code clones in Python. So clone detection is divided in 4 clone types. First, we have type 1 or exact clones, which correspond to identical pieces of code spread around the code base. The second type of clones is renamed clones, where we have variable renaming across the clones. The third type of clones, or near-miss clones, take into account a larger modification of the clone, as for example here, changing a binary sum operation with a unary sum operation. And the final type of clones, type 4 clones, corresponds to semantic clones, which are larger transformations of the code farther away from code structure and syntax. And in this example, we have the case in which we are adding 10 to a variable with a cycle or with just an operation of 2 numbers. The work of clone detection focuses on the first 3 types of clones, and the majority of body of work is in the detection of type 1, 2, and 3 clones. Identification of clones is based on 3 major approaches. The first approach, on the textual identification, takes the code base as a string and compares strict fragments around the code. An optimization of this approach is the analysis of the code as a tokenized version of the clone, and this basically accelerates the performance of the code. A second approach uses a tree-based representation of the code, in which we take the code base and represent it as a tree, usually based on the eCST of the code, and then find sub-tree structures similar in the different branches of the tree. The final representation, similar to this, is a graph representation of the code, in which we represent the code as a graph and then try to identify subgraph structures that are similar across each other. Finally, and more recently, we have approaches that are hybrid and are based on 2 or more of these approaches. In particular, our approach out of step is a hybrid approach combining a generalized tree structure with a tokenized version of the code. The current landscape clone detection detects different approaches, and from these approaches, we identify 3 major drawbacks across them. The first one refers to the shape of the languages, as most current clone detection techniques are based on a single language and they don't take into account the different forms and shapes of the different languages. Additionally, together with that, we have that the abstraction level of the code is not so high, and therefore we are not able to identify clones across languages. And finally, we identify that most existing tools are based on a single language and legacy and common languages, and they are not up to date with current languages, and we would like to be able to present a tool that can take into account more modern programming language approaches. So, the setting of our work is on the analysis of mobile apps, in which we have applications that can be developed into different code bases. Here we have a representation of the same application in different programming languages for the different existing platforms. The problem with this is that as multiple development teams are working on the individual parts of the application, then we have feature divergence across the single application. So the question here is whether we are able to identify clones across different programming languages, and in our particular case, across different programming languages for mobile apps. Step is able to identify clones across these programming languages, but as you can see, the identification of clones across these languages requires a larger abstraction of the concepts, as for example, in type 1 clones, exact clones are not exactly the same, so we need to abstract exactly the operations that we are executing. And as with most current tools, our tool focuses on the identification of type 1, 2, and 3 clones. The clone detection process in our case begins with the definition of the language's grammar. Here we take the language grammar and process it using an handler to be able to extract the standard lexer and parser of the language. from that extraction, we construct our own tree representation for the language called eCSTs, and from that we can analyze the different code clones to identify type 1, type 2, or type D clones in a single code base or across code bases written in different programming languages. eCSTs stand for Enriched Concrete Syntax Trees, and they are a representation and an abstraction of the programming language and of a program in a tree form. So, as an example, let us take this code snippet in which we can start identifying the different parts of the code. Here, all our trees start with a root of a file node, as we are able without a step to detect clones of complete applications and complete files. So this is the root of the extraction of all the code in a file. So then we have the definition of the function declaration, which is split into the declaration part and the implementation part, so the function body. And for the declaration part, we have the representation of the parameters, and then for the body part, we have the representation of each of the assignments. Note here that the different instructions in the body are represented as different nodes. And here we have a larger abstraction of the nodes, for example, in the case of loops, where we can when we can abstract away from this specific for structure to a loop structure that is more general and can compare to other types of loops and iterating processes. Additionally, in the definition of loops, we have these transitory nodes called advanced nodes, which are able to give a larger structure to the code base, and this is done to be able to compare across languages that have a flatter structure, as it is the case of Dart, and larger and richer grammar structures, as the case of Kotlin. So in addition to the introduction of universal nodes, which represent the syntactic grammar rules abstracting the languages in the programming context, and advanced nodes, which are used to be able to give a structure to our code, nodes are also enriched with a particular token. Tokens have the definition of the text from which the token is coming from, so basically the relation between the text in the code and the actual token in the tree structure, the line and the column in which the text appears, so in which the token appears, and the clone type of that particular node. And the final type of node is that of stop nodes. Stop nodes are used in eCSTs to be able to analyze code fragments across different parts of the trees. So we can identify, for example, a function definition that is detected in a different part of the tree and not in exactly a branch of the tree of the same shape. In this example, we have two function definitions in the two programming languages, in Kotlin and Dart, and the stop nodes between them are able to identify the function declaration for each of them, comparing those, and then the function body of each of the functions which we compare. And we will talk about this example later. The first part of the comparison process starts with the analysis of the root nodes, and root nodes are abstracted away with universal nodes. Universal nodes let us abstract away one particular part of the code. For example, here the definition of the types, abstracting away the different types of a parameter or a function as just a single type node, and they are defined as similar. This definition of similar nodes in universal nodes is given beforehand to the code based on the use of the syntactic constructs in the language. Once we have the similarity of this, identify the similarity between universal nodes, then the second step of the process is to be able to analyze the text in the tokens for each of the nodes. Based on these two steps, then we can define what is the clone type associated with the analysis on the node type and on the token comparison. So if the nodes are not similar and the tokens within are not similar, then we have no clone. If the nodes are the same type and the text inside the nodes is exactly equal, we have an exact clone, so they are type 1 clones. If the nodes are the same type but the text within the nodes is not equal, we have a type 2 clone. and if the nodes are just similar and the text within them is not equal, then we have a type 3 clone. Additionally to this, we give a weight to the different type of clones to make sure that we are detecting the most similar clone for the code fragments. And the metric to weight clones is given as here in the slide, giving a larger importance to type 1 clones and a lower importance to type 3 clones. As an example of the clone detection algorithm in our work, let us think about the two function definitions that we saw in the example before. So here we have two functions defined in Kotlin and in Dart, and simplify the structure of the eCST for those two particular code fragments. The first part in this step is, as we are declaring functions, we divide them in the stop nodes. So analyzing the function declarations and then the function bodies. The analysis of the function declaration takes into account the analysis of any function from the Kotlin code to any function of the Dart code. And here we identify two type 1 nodes between the functions get A and then between the functions get B, identifying the functions get A and get B as type 2 clones. We have a lower priority according to our metrics. They have a lower importance, so the identified clone is a type 1 clone. As you can see here, then we pair function get A with function get A and function get B with function get B. Then we have to analyze the body of the functions, the second part of the stop node. And here we have the reverse case as we had before. So here function get A has a type 1 clone, function get A in Kotlin has a type 1 clone with function get B in Dart, and function get B in Kotlin has a type 1 clone with function get A in Dart, while having type 2 clones identified for the bodies on the other situation. Here we identify the two type 1 clones across the two different code bases, detecting the get A function in Kotlin as a clone of type 1 with the function get B in Dart, and function get B in Kotlin as a type 1 clone of function get A in Dart. As we have the revert cases, the lower nodes, they start moving forward or moving up the tree, the clone type to their parent nodes, so it's the function body nodes get the same type of the lower nodes, and then we move forward that up to the function declaration in such a way that we identify effectively as nodes get function get B in Kotlin and function get A in Dart, and function get A in Kotlin with function get B in Dart, as these are the stronger nodes in their bodies. Now that we have seen how the process of clone detection works, we will validate their work. The validation is divided in three parts. The first part focuses on the correct identification of clones across the different language features for each of the languages, Kotlin and Dart. Then we move the validation to see how the process works in larger code bases. First, taking the code base of sorting algorithm, which are known algorithms where we can effectively identify if the clones identified by our step are correct or if they are false positives. And then we move to even larger applications analyzing complete mobile apps. The full implementation, the full validation of our work is accessible from the online appendix. For the clone detection across language features, let us think about the loop structure. Here, finding a loop in Kotlin, a for loop in Kotlin and a while loop in Dart. The eCST structure of these two code pieces is as follows. And here, out of steps is able to correctly detect the type 1 clones across the first assignment in the structure, detecting correctly as a type 1 clone. And then inside the loop body, it is also able to detect as a type 1 clone the assignment of the sum variable. The loops themselves are detected as type 3 clones. As these are similar nodes, then they are part of that category. But furthermore, since the condition on the loop is different, then those two conditions are also detected as type clones, which then are pushed forward to the upper nodes on the tree, the loop declarations, and therefore the loops are declared as type tree clones. For the evaluation of the mobile applications, we extracted 52 mobile applications, 26 applications developed for Kotlin and 26 applications developed for that, making sure that for each application, the same version of the application was developed under the umbrella of the same organization to be able to ensure some type of feature accordance across the applications. We have different types of applications that we were able to extract, so in the purpose of the application and in the size of the application, as well as in the size of the development product and the level of expertise in the product. As we can see, out-of-step is effective in identifying clones across the different applications. We are able to validate the type 1 clones and some of the type 2 and type 3 clones for the smaller application, but as the size of the application grew larger, the manual identification and verification of these clones was harder, and therefore we don't have the precision metric here. The takeaway message of this presentation is that out-of-step is able to raise the level of abstraction in the representation of the code, presenting eCSTs and being able to identify similar structures from different language abstractions. And this enables us to compare such abstractions and compare them across languages in such a way that we can effectively enable across language comparison and the clone identification. Our tool is indeed able to analyze polyglot systems, so systems that are developed in different languages. The focus of this presentation was on mobile apps, but we can introduce more languages to out-of-step and be able to extend the analysis to those languages. Currently, we have 6 working languages with the implementation of out-of-step. But furthermore, clone identification for out-of-step was effective, as we were able to detect clones with a precision of 79% on average, finding the lowest average as 65% and the highest average at 84% in the non-domain application and in the language features application. However, the work with out-of-step is not complete, as we were able to identify clones across larger code bases, and we want to identify clones for full model applications, then we need to extend the detection algorithm to be able to take into account graphical user interfaces and different frameworks used by the language in the development of mobile apps, as these are rarely part of the standard language definition and therefore are not captured by our grammar analysis and the creation of the eCST. So this will be a point of extension for our step.